Okay. One application of this escape velocity equation that we just developed is some pretty Einsteinian physics. Suppose 2g m over r, just for a point of comparison, if we plugged in the mass of the Earth and the radius of the Earth, the escape velocity from Earth would be 1.12 times 10 to the 4 meters per second. The escape velocity from the sun, if we plugged in the mass of the sun and the radius of the sun, would be more than that because the sun's bigger than the Earth. .18 times 10 to the 5 meters per second. Okay. What if we found a star such that it was the same size as the sun, but much more massive? It's possible that some super massive star might end up getting us a value from this calculation that's greater than 3 times 10 to the 8 meters per second, which isn't actually real. That's the cosmic speed limit. Nothing can go faster than the speed of light, 3 times 10 to the 8. So this object, whatever this is, some mass and some smallish radius, is an object from which it is not possible to escape. If you are in its gravitational pull, then even light cannot escape this because it can't go fast enough to do so. The well of potential energy is too deep. We can't put enough energy in to get out. And I think at this point you know that we're talking about a black hole. If we solve this backwards, if we set that the speed of light is the limiting value, and we solve for the radius, let's see, so we square both sides. R would be 2gm over c squared. This is called the Schwarzschild radius, and it's the smallest radius that a star of mass m could have before it becomes a black hole, or it's the point of closest approach to a black hole. There's actually some sort of hand waving going on here. The calculations around the black hole are super intense. There's we have to modify the potential energy function a little bit, and there's relativity involved, and it turns out actually that we end up with the same algebraic answer that we would if we had actually done this. So it's we get lucky a little bit. There's some information in the book about detecting black holes and how we can leverage Kepler's laws to do that. But this is the sort of conceptual underpinning for the fact that they theoretically could exist, and in fact, we've found them now, and even photographed one. If you saw that in the news, check that out.